Welcome, everyone, to our digital science classroom. I am so incredibly excited you're joining us. Today, we're going on a totally mind-blowing field trip right from wherever you're sitting. We're diving into an explainer on a topic that sounds like pure magic, but is actually pure, amazing science. We're going to trace the unbelievable journey of a simple, tiny grain of sand and find out exactly how it becomes the most complicated piece of technology on planet Earth.
What if I told you that your smartphone, your gaming console, and the smartwatches we wear are all powered by beach sand? It sounds crazy, but the brain of every piece of tech you own is made from a special ingredient found inside ordinary sand called silicon. But how does a handful of gritty, yellow beach sand transform into a super-fast, modern computer chip? Well, grab your imaginary protective suits, kids, because today we are going inside the clean room to trace this incredible scientific journey.
Now, before we build anything, we really need to know why we use silicon in the first place. Why not just use copper wire? Well, copper is an awesome conductor, meaning electricity flows through it instantly. But if we built a computer chip out of copper, all the electricity would rush through at once. Every single switch would light up, and the computer wouldn't be able to process anything at all. It'd just be a very expensive paperweight. Silicon, on the other hand, is a semiconductor. It allows us to perfectly control the flow of electricity, acting kind of like a tiny gate that we can open and close exactly when we want to.
So our absolute first major challenge is extracting that silicon from the sand. Beach sand is mostly quartz, which is basically a super tight combination of silicon and oxygen bound together. To separate them, we have to turn up the heat, and I mean really turn up the heat. We take the sand, mix it with a form of carbon, and dump the whole thing into an electric arc furnace heated to a blistering 2,000 degrees Celsius. That is literally hot enough to melt steel. At this extreme temperature, the carbon acts exactly like a chemical magnet. It pulls the oxygen right out of the sand, leaving us with a pool of glowing, molten liquid silicon.
Okay, that sounds great, right? We have our silicon. But here's the catch. This new metallurgical silicon is only about 99% pure. Now, in the everyday world, 99% is an A+ grade. You'd be thrilled. But in the microchip world, 99% is incredibly dirty. To make computer chips work without crashing, we need what scientists call 99's purity. That means our silicon must be 99.999999% pured.
To picture exactly how ridiculously pure we're talking about, imagine a giant Olympic-sized swimming pool completely filled with billions and billions of blue marbles. To achieve 99's purity, you are only allowed to have a single red marble of dirt in that entire massive pool. Anything more than that, and our electrical signals will crash. So, as you can guess, we have a whole lot of cleaning up to do.
To get it that clean, we have to do some pretty extreme chemistry. First, we take our 99% pure solid silicon and react it with a hydrochloric acid gas. This actually turns the solid rock into a liquid. Then we boil it. Just like boiling dirty salt water leaves the dirt behind while clean steam rises up, the heavy metal impurities are left sitting at the bottom of our tank. Finally, we take that super pure gas, mix it with hydrogen, and let it rain down onto heated rods inside a reactor. The gas magically turns back into a solid, building these massive, ultra-pure rods of silicon. This whole thing is known as the Siemens process.
All right, so our silicon is finally pure enough, but now we have a completely new problem, and it's all about its structure. Right now, it's what we call polycrystalline. Imagine a wall built out of jumbled up, broken pieces of glass facing every which way. If we try to shoot electrons through that chaotic mess, they'll just crash into all those random boundaries and lose their energy. What we actually need is monocrystalline silicon. We need every single atom to sit in a perfectly organized repeating grid, exactly like a marching band lined up in perfect, straight rows. To force our chaotic silicon into this perfect marching band formation, we use something called the Czochralski process. We take our pure silicon and melt it all over again in a special quartz bowl at exactly 1412 degrees Celsius. Then comes a total science magic trick. We take a tiny, perfectly organized piece of silicon called a seed crystal and lower it until it just barely touches the surface of the molten pool. As we slowly spin this seed and pull it upward, the liquid silicon freezes onto it, perfectly copying that organized marching band structure. We end up pulling out a massive, heavy, completely organized cylinder of silicon called an ingot.
Now we have this giant, heavy, glass-like log of perfect silicon. But obviously, you can't build a microchip on a giant log. We need perfectly flat surfaces. So how do we cut it? We use a wire saw, which operates kind of like a high-speed egg slicer. We use an unbelievably thin, high-tension wire moving at super high speeds, coated in a liquid mixture filled with microscopic diamond particles. The diamonds gently grind their way through the hard cylinder, slicing it into lots of incredibly thin individual discs called wafers.
And when I say thin, I mean absolutely paper thin. These wafers are roughly 725 micrometers thick. That is right about the thickness of a standard credit card you'd find in your parents' wallet. But the wire saw leaves microscopic scratches on the surface, and we need this surface to be utterly flawless. So, using a process called chemical-mechanical polishing, we press the wafer against a rotating pad and use nanoscale abrasive particles to gently rub away those scratches. We do this until the surface of the wafer is atomically flat. It is perfectly smooth on a microscopic level.
Before we can draw our tiny computer brains on this beautiful flat wafer, it has to be absolutely spotless. Think of this next step like an extreme 3-step car wash for our silicon canvas, known as the RCA clean. First, the wash uses chemicals to create a tiny layer that actually pushes any organic dirt particles away using electrostatic forces, exactly like two magnets pushing apart. Second, an acid bath is used to trap and dissolve any stray metallic atoms that might be hiding. Finally, a gentle acid dip strips away the top layer, leaving us with a pristine, perfectly clean canvas ready for building.
Okay, our canvas is ready. But how do you draw the tiny pathways of a computer chip when they are way too small to even see with a normal microscope? The answer is photolithography. This is essentially the science of printing with light. We coat our wafer in a special light-sensitive polymer. Then, we shine a highly specific type of light through a stenciled mask, projecting the blueprint of our chip straight onto the wafer. Because the details we're drawing are so incredibly tiny, we have to use extreme ultraviolet light, or EUV. And the craziest part? To make it work, we have to do the whole thing inside a complete vacuum.
Creating that extreme ultraviolet light sounds like something straight out of a sci-fi movie. Inside the machine, tiny droplets of liquid tin are fired through a chamber at 50 meters per second. As a droplet falls, it gets blasted by a high-power carbon dioxide laser twice. The first laser pulse smacks the droplet and flattens it like a tiny pancake. A split second later, a second massive laser pulse vaporizes that flattened tin into a glowing, highly ionized plasma. That glowing plasma emits the exact 13.5 nanometer EUV light we absolutely need to print our chips. That incredible flash of EUV light bounces off perfectly smooth mirrors and projects our chip design onto the wafer. Now, the scale we are working at here is truly mind-blowing. We are printing features that are literally smaller than a biological cell. To give you an idea of how insanely small a 2-nanometer print actually is, if you pulled a single hair out of your head and looked at how wide it is, you could fit thousands of these tiny printed features perfectly across the width of that single hair. No way, right?
So, we're printing incredibly small things, but what exactly are we printing? We are printing transistors. A transistor is just a microscopic electrical switch. It controls the flow of electricity, kind of like a tiny faucet that turns water on and off. But as we made these faucets smaller and smaller to fit more of them onto a single chip, they started to leak electricity. To fix this, scientists invented something brand new, and it's called the gate-all-around transistor.
Here is exactly how we solve that annoying leakage problem. In old transistor designs, the gate, which is the part that squeezes the channel to stop the electricity, could only wrap around 3 sides. Electricity would actually sneak out the bottom, wasting your phone's battery and causing it to heat up. The new gate-all-around, or GAA, architecture completely changes the game. Instead of one channel, we suspend incredibly thin ribbons of silicon and stack them on top of each other, just like a multi-level highway. Then, we wrap the gate completely around all 4 sides of every single ribbon. This traps the electricity and gives us absolute perfect control.
To build this awesome atomic-scale architecture, we first grow alternating layers of pure silicon and another material called silicon germanium. Next, using that EUV light we talked about earlier, we carve these layers into tall vertical fins. Then comes the magic trick. We use a special chemical to dissolve only the silicon germanium, completely leaving the pure silicon layers behind. They're left hanging in mid-air, like tiny suspended microscopic bridges. Finally, we carefully wrap the gate material around every single suspended bridge. And we do this billions of times on a single chip.
So, what does this all mean? The absolute crucial point I want you to take away from our explainer today is that science is all about seeing the invisible potential in ordinary things. We took dirty, gritty beach sand, stripped it down to its atoms, purified it to near perfection, grew a single giant crystal, sliced it into credit cards, blasted 10 with lasers, and built microscopic floating bridges. All so you can play games, learn new things, and connect with the world. The next time you are playing in a sandbox, just ask yourself, what other amazing secrets are waiting to be discovered right under our fingertips? Keep questioning, keep learning, and I'll catch you guys in our next explainer.